Cool, I guess we can get started. So today we're going to talk about visualization. So first thing is, you've noticed all that this is an absolutely awful data set, right? It's kind of cool how something so ridiculously simple can be absolutely horrible to work with, especially if you're limited to the linear models that we have in. So going to the lab yesterday, it was really nice to hear people reason about this data set, spending time thinking about, oh, you know, there's something happening here, maybe I'll split this up, I'll do this, and so forth. The whole reason that you could reason about this was because you could see it, right? If this data set was ridiculously high dimensional or very strange, you didn't have a visualizer for it, you couldn't reason so easily about it, right? And then it would be really hard, and actually coming up with ways of fitting that would be pretty much impossible, right? So today we are then going to take that notion and say that, you know, being able to look at data is super useful. So how can we then think about methods that helps us extract visualizations of data? So if you would take a course in visualization, it's going to start with something like this. They're going to show the tube map. Generally it's of London, but I show my home, no, it's not my hometown, but I lived there for a very long time, of Stockholm, which is the same thing. You have the tube map. The tube doesn't go at all like this. People draw it in this way because you have a task, you're supposed to navigate the system, and then it's much, much easier to see the map like this. We're not going to do that because that would require me to know lots about data. We could probably do that if I knew everything about proteins and I was an expert on that. I could talk about how you visualize proteins. I don't know much about proteins either. So we're going to try and do this algorithmically and quite general. So for this lecture, there's going to be quite a lot of derivations that I'm going to be reasonably sloppy with. There is therefore a long, if you're interested, PDF which contains all the math that I will talk about today that you can look at if you're interested. So that will be up on the course webpage together with this lecture. Cool. So instead, we are going to talk about how you can visualize data in general. And I like the notion that Neil used, where he said that data science is not like programming. Data science is like debugging, right? And there was this story about walking down the road, finding a hard drive, not even knowing what the file system it was on, but knowing that there's something important on that. And now you need to start poking that. And visualization is one of the tools that you use this for in data science. Cool. So let's talk about data then. So here, my dog, Selma, is very, very cute. And this here is an image. So now this image, I think, is something like 3,000 by 4,000 pixels big, right? That means that this image lies in a vector space that's 3,000 by 4,000, right? So very, very high dimensional data. Very cool that we can actually interpret this because we have a good visualization for that type of data. However, if I would just pick random points in the same space as Selma lives in, most likely I will get something like this. This is just a random sample from the same thing. I would probably have to draw an enormous amount of samples to get anything that looks like a natural image back, right? Most of that space of images is filled with nothing, right? So this is something that we're going to try and exploit. So we're going to try and think about two concepts of parameterization of data. We're going to think about the parameterization of the representation. So that means, how is the data given to us, right? And most commonly, this parameterization is determined by how you've measured the data, right? The reason why Selma looks like that is because I used a camera, right? And the camera measured the light at the pixel. But now we're going to think about another representation, the one we're really interested in. And that's what I'd refer to as the canonical representation of the data itself. And that is the thing that parameterizes how the data varies itself. Right? So in this representation, everything that I would pick would be a valid natural image. Right? So if I would have this representation, I would understand a lot more of the data itself, right? And it would be much lower dimensional. There's no way the natural world has 3,000 times 4,000 degrees of freedom. It doesn't, right? It has a lot less than that, right? So if I could extract those parameters, I would have a much clearer idea of how the data works. Cool. So we're going to use then the notion of a manifold. So the definition of a manifold is a topological space that near each point resembles the Euclidean space. So what does that mean? Well, I like this sketch. So here is a topological space. It's a circle. It's a one-dimensional space embedded into the two-dimensional Euclidean space. Now, on that space, I have some form of measure. I have some form of distance where I move along that circle in this way. Now, if I would take the Euclidean distance, the one that doesn't take into account the data itself, this would be the canonical representation of the data. If I would take a distance that's actually a part of the space that it's embedded in, so the representation itself, now that's the red distance here. And now we can see that the green and the red distance is very different. However, what the manifold assumption, the definition that we had previously, it said that near each point, it resembles the Euclidean space. So if I now take a very close point and take the distance, we can see that those two are very similar, right? So that's the notion that we have some data. If there's some notion of smoothness, most likely if I take another image of Selma, or if I had an iPhone that takes like 5 pictures at the same time, most of those images would be very close together, right? And now those would be like these points here. But then if I take a photo the next week or outside, you'll be much further away, right? And then the Euclidean distance between them will not resemble the distance along the parameterization of the actual data. Okay? So what we're going to do, I would love to be able to say, cool, let's now go and find the natural or the canonical parameterization of images. If I could do that, I would have solved computer vision, right? People are still working on that. So we're going to work on something much simpler. The examples that we're going to use are going to be things like this. So here I have a 3-dimensional manifold. This is a classic data set called the Swiss roll. And now our aim is to see some data like this, possibly, or most likely it's going to be a little bit higher dimensional, so we can't actually see it, but I want to recover something like this, right? And now in this space, every point that I pick here lies on that Swiss roll, right? Cool. So what we're going to talk about then is to say, how can we reduce the dimensionality of data to somehow visualize it? Can we think about these manifolds to think about how can we unravel a manifold. So take that Swiss roll and then bend it up like this, right? And then we are towards the end of the lecture. I'm going to say all these things, and then I'm going to say, actually, this is really hard, and I'm going to introduce a problem like we do in this course, right? We don't give you solutions, we just tell you everything that's problematic. And then that's going to lead to statistical models, which is going to lead to the lecture on Friday. Cool. So let's talk about dimensionality reduction. So to introduce this, we are going to use something called similar matrices. So it's a very simple concept that you probably know about. So I have two linear maps, MA and MB, and I got a transformation matrix P. Okay, so this sketch here just shows how all these things hang together. So if I have a point X represented in A, now if I perform the linear map on that, plop, that's like going to MAXA. Now I can do the same thing if I got the point in B. I can apply that linear map, and this transformation matrix P just moves between those two spaces. You can think about it as a rotation, effectively. Right? Okay, this is how these matrices hang together. So what I want to get to with that is that now I'm just going to expand that. So I have the point in XB. I'm applying this linear map MB. Now that's the same thing as doing it in A, MAXA, and applying this transformation matrix. I can do this step once again, and now I end up with this result. And if this is true, that means that I can write MB and MA like this with this relationship. This is true, then we call these two matrices similar. Okay? You've seen one of these tons of times, and that is the Eigen decomposition of a matrix. Right? We've seen this transformation, and what this is, it's two matrices that are similar. So it's A, which is similar to a diagonal matrix capital lambda. Okay, we've seen this, hopefully. Please nod heads. So yeah, very good. Cool. So two similar matrices. It's similar to the matrix that are diagonal. And this we're going to use tons. So the cool thing with the Eigen decomposition is that there's something called the Spectral Theorem. And the Spectral Theorem says that all symmetric real matrices have a diagonal matrix which they're similar to. So if we've got a symmetric and real matrix, we can always do the Eigen decomposition. And further, it means that we can write this type of decomposition of a matrix. So we can write a matrix, any real symmetric matrix, as this. So this is a sum of rank 1 matrices. And this is something that we're going to use. Okay? Does that make sense? So you have to think about, we're taking, how is it? We're taking this times this, right? For the vectors. So we get these matrices, and we just have a scalar factor on them the whole time. Right? Cool. So then the theorem that we're going to use to do dimensionality reduction is this. It's something called the rank nullity theorem. So if I have two vector spaces, A and B, I have a map from A to B. This says the dimensionality of the space A, so this is the dimensionality of the representation, is equal to the rank of the map, that is the image. So that's, if I take a map, this is all the possible output values that I can get from this map, plus the nullity, which is all the values that map to the same value, so the null space of this. So now, what we're going to try to do is that, can we find a map such that the kernel or the null space is actually the part where the data have no variations? then I can apply this map to the data, and I've effectively uncovered only the subspace where the data has variations. That's the type of thing we want to do. Does that make sense? Yeah. So I have some data. Let's say that we have the Swiss roll, right? So it only varies along this thing. Now I want to apply a transformation to that, so that when I've applied the transformation, it looks like this, right? Now that means all the holes between the Swiss roll is now part of the curve, like the null space. It's the things I mapped away, right? Cool? Right, so the simple example of this in the linear case, which hopefully you've seen, is that, say that I now have this type of data. So I got something in 2 dimensions that varies across 2 dimensions. And now what we would want to do is that we would want to do something like this, right? We would apply a transformation that transforms this data such that it now lies like this, right? Now, in the previous case, with the rank nullity theorem, I said, well, there's a part, we want to find a mapping so that there's a part of the space that doesn't vary at all. What we want to do in the real world is that we want to find something so that we have the directions where it varies the most. And you've seen this as PCA. We've all seen PCA, have we? Hopefully, ish. Okay, so if we haven't done that, it's super simple, right? You remember we said that I have a matrix. A symmetric matrix always has a diagonal form, which is similar to, right? So now if I take some data that's centered, compute the covariance matrix of that, then I can find the diagonal form of that. The diagonal form will now have no covariances. The mapping of that will be this mapping, right? This mapping here, the dimensions don't covary. In this one, they do covary, right? And that's called PCA. Oh, haha, hang on. Oh, I have no battery left in my computer. It's completely dead. And I thought it's a bit, oh, there we go. Cool. So what we're going to do is that we're going to try and extend this notion a little bit and think about a scenario where we might not even have vectorial data. So what we have is that we have data which says something how similar things are, similar or dissimilar, the same notion. So let's say, for example, I'm going to have a dinner party, and now I need to figure out how people should sit at the table, right? So I want people to sit close to people that they like, right? So now what I can do, I can create a matrix which says how much everyone in my group of friends like each other. Now, that has no vectorial representation. The only thing I have is a notion of similarity, right? And then what I want to do is that I want to go from that to an actual vector representation that says, you're going to sit here, right? So that's what we're going to try to do. So we can think about this as this. So remember our manifold notion that we had before, right? I can take this kind of data, and I can also represent this data such as a matrix like this, which would basically say something about how close each point are to each other. Now, let's forget this. Let's throw this one away and say this doesn't actually come from vectorial data. We only have this from one reason or the other, right? And now what we want to do is that we want to create something like this that we can actually look at. This matrix here is a little bit messy to look at. Can I create something like this? We can look at it, we can do machine learning, we can do all sorts of cool stuff, right? This thing here is a bit messy, right? So that's our task. So what we're going to do is that we're going to say that we are going to try to have, or we've been given, or we've calculated, we've gotten some form of matrix here, which is an n by n matrix which says how similar, dissimilar, is each point to each other, right? Okay, and now we want to recover a vectorial representation that matches this. Okay, so what we want to do is that we want to find a matrix D such that this D comes from some vector representation Y, right? So that we can take this vector representation Y and plot this. But what we're going to work with, we're always going to work with inner products. So the notion here, I showed this in the worksheet, but the notion here is that there's this matrix Dij, which each element is the Euclidean distance between 2 points. Now, we're going to work with something called a gram matrix, where the gram matrix is at each ij element the inner product of 2 bits. Okay? So now you can kind of see how Dij is just these elements, it's just lots of inner products. So what I can actually show is that I can write each of these gram matrix elements just as a function of distances. So distances and inner products are exactly the same thing, right? Okay. So the objective then that we have is that we've been given this matrix delta, which doesn't come from a vectorial representation. We want to now find this D, which we can calculate from a vectorial representation, such that we minimize the distance between these 2 matrices. Okay? So we're going to do this using the Frobenius norm between these 2 matrices. The Frobenius norm is really, really simple. It's just the extension of the normal Euclidean vector norm to matrices. So a vector norm you can write such as this. So the only thing you do, you have 2 indices, or you have the vector norm P2, which is taking each element of the matrix to the power P, and then you sum all of them, and then you take 1 over 2. So the Frobenius norm is the one that's 2, 2. So you square each element of the matrix, sum them up, and take the square root of that. So we have these 2 matrices. One of them we've been given, the other one we want to find. We want to find this one that matches this as best as possible. Okay? So now, the way we're going to do this is that any proximity matrix will be square and symmetric. Right? That makes sense, right? If it's not, we're in trouble. Then I have guests that don't like each other in a weird setting. So if that's true, that means that there's a similar diagonal matrix to any proximity matrix. Okay? So now, if that's true, if there's a similar diagonal matrix, what would the Frobenius norm be of a diagonal matrix? Well, it's super simple. I just square each term on the diagonal because everything else is 0, and I sum them up. Right? So that is the trace of that matrix. So now the Frobenius norm is therefore, for a diagonal matrix, it's just the trace of the square of the elements and the square root of that on the outside. So this is our setting. Then coming back. So what we want to do is then take the trace of this matrix here. Now, so what we're going to do this is that we're going to both diagonalize these 2. So we're going to take the similar diagonal matrix, this one here that we have. So V is the eigenvectors of this, and this one has Q. And then what I'm going to do is that because it's the trace, I can do the transformation of this. That's still a similar matrix, right? So the trace is still the same, doesn't do anything. Now I'm going to move these D's in. And what we get that is this. Now we can see that this here is just a rotation matrix. So the transpose of that is it's the same as its inverse. So I'm rotating, then rotating back. So these are just going to disappear. And I end up with this expression. Okay. So now what I have is that I'm trying to minimize a diagonal matrix to this. This, I have no clue of what it is, right? What should we choose Q and this to be? Think about this. So I want to minimize the sum of each of these elements here. Would it make any sense to put off to make this thing here non-diagonal? So now I'm subtracting terms. This one's diagonal, so it has only zeros. So I would never ever want to put things off the diagonal, right? The best thing I can do is to cancel diagonal terms in this one to make this as small as possible. So the thing I should be doing is to put B and Q to be the same thing. Now I just end up with two diagonal matrices where I can just cancel out things on the diagonal. Right. So if I do that, so if we effectively pick D to be equal to Q, well, these things now cancel. So now I just have these two diagonals, which I'm canceling with each other. Great. So if I now do this, and I want to find a lower dimensional representation of this, which element should I cancel? Well, I should cancel the really large element, right? Because those are the things that's going to appear in the sum, right? So if I want to pick a d-dimensional, the best d-dimensional approximation to the similarity that I wanted, I should now pick the diagonal of that matrix to match the top biggest elements in the proximity matrix that I have, that I diagonalize. So if I do that, then the error term, the things I get left, the things I can't cancel, because the D here will be 0 for those. If I want to pick a rank D, then the error that I have left is just the sum, the square root of the sum of the remaining eigenvalues in the proximity matrix. So if I do this, now I've found a D, which has a guaranteed rank, because I picked that rank of this matrix. And now the last bit is that we know that D was just this inner product matrix. So now I need to find the representation back. So now I say that D was this inner product of some representation that I want, which was equal then to whatever eigen decomposition that I picked, or the eigen decomposition of the proximity matrix. If I do this, now I can clearly write it like that. I can split this up like this, and that means Y, the representation that I have, which is now has D dimensions, which is equal to the eigenvector times the square root of the eigenvalues. This was a very, very long-winded way of reaching a very, very simple result, right? But I hope that makes sense still. So let's do an example of this. The classic example that people give you is something like this. So here I went onto a map and I took the distance between some cities: Manchester, Oxford, London, Bristol, Liverpool, and Birmingham, right? So this here is a proximity relation. I have no idea where these things actually are. Well, I do, but this was what I was given. So I've been given some 6-dimensional data. Now I can apply this technique, and then what I can do, I can get something like this back. Right? This here is a geometrical configuration that respects that proximity. Right? So now you can see it's flipped on its head simply because the largest variation is north-south, right? And the next one is east-west, right? The next thing, which is kind of funny, if I actually look at the eigenvalues of this 6 by 6 matrix, it actually has a tiny third dimension. Why would it have a third dimension to vary against? The AI for ER students should know about this because this is my standard joke. What was I talking about yesterday? Yeah, flat Earth, come on. Right? So there's a third degree of variation because the Earth is not flat, right? If it would be two-dimensional, then we wouldn't have a third dimension, right? We're trying to find a linear mapping to this. It's a slight bend over this country, right? So that's why it has 3 components, but we just pick 2, right? Cool. So this is a really, really powerful thing that you can do, because what you can now do is you can take all sorts of measurements of similarity, and you can go from that to this, right? And then when you've gotten this, you can do whatever machine learning that you want on this. You can fit generalized linear models, you can do all sorts of stuff, right? And that is really, really useful, right? It's a bit of a contrived example because I clearly took these distances off a map and then went it backwards. But say if you don't have data that's like this, right? Now you can start actually visualizing this. This says a lot more than that, right? That's the point. If you're given this or you somehow measured this, it's really, really hard to reason about. But that thing here is much, much easier to reason about, right? And especially if that matrix starts growing now, right? So a lot of these techniques comes from, when people do a lot of this work, comes from psychology, but they do different kinds of measurements like this, and then they want to, they generate these kind of plots, then to try and figure out if the relationship between everything in a data set, where this one is just pairwise, right? Cool. So now, if you're interested, so in this case, what we did when we were completely linear is that we diagonalized this matrix. Oh, I think I got the transpose the wrong way around. YYT, I think it should be. But we diagonalized an n by n matrix. We had an n by n problem that we solved. If you do PCA, you do it the other way around. So now you have a d by d matrix. You take a covariance matrix instead. It turns out that the solution that I just gave you is exactly the same solution as PCA. It will be exactly the same, except for that you solve a much, much higher dimensional problem. So why would I ever want to do this? Well, the reason why you want to do this is that, let's go back to think about the manifold, right? So we have this notion now that I can take a similarity measure, and then we can get the geometrical embedding from this. So the definition of the manifold was as a topological space that near each point resembles a Euclidean space. Well, we can measure, what this says is that if I have some vectorial data, I can measure the local distances faithfully by doing the Euclidean distance. It's just going to go far away. I can't, right? That's effectively what this says. So what we could do is that, let's take this thing again. If we would apply the technique that we used before, if this was cities in some cities, and we took the Euclidean distance between every point, and we will apply this thing, nothing would happen. We would get this thing back again, right? But what we said, what the manifold assumption said, was that actually, if I take a local distance here, that one's actually valid. It's a valid distance. It's just the distance between the blue and the red won't be valid, right? That would not match the manifold distance. So what we could do is we could compute, effectively what we have is that we got this proximity matrix, which is locally valid. It's valid for some points, but it's not valid for all. And what we could do is we could use a technique to come up with how can we fill in all these values by some mean. And if we could fill them in, then we could just apply the same technique, right? So think about how could we do that? So say that I take this Swiss roll and I compute the local distances. Well, now you kind of saw what I was going with. I compute the local distances between points, and I want the distance from this point to this point. How could I get that faithfully, not this distance? Dunk, 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 dunk. Right? So if I compute it like this, right? So what I want is that I want the distance from the two black things there, the black circles. If I compute the Euclidean distance, it's wrong. But locally, the distance is correct. So what I could do is that I compute this graph that we had, and then to compute the long distance between 2 points that are not connected, I can do a thing like the shortest path, for example. Right? If I do a shortest path between them, now I fill out this matrix and we can apply NDS on it. Right? So that was exactly how I generated this one. So I took local distances here, generated a sparse matrix, but the sparse matrix was connected, and then I ran shortest path between every data point, filled out the distances, and then I applied NDS, and I got this back. Right? Now you can come up with tons of different ways of filling out that matrix, but now you have the means of calculating an embedding from them. Right? Does that make sense? Yeah. It's not a particularly tricky thing to do. This paper that did this is now 20 years old. I have no idea how many citations it is. The paper is 4 pages, and it should be about half the page. It's absolutely brilliant that no one thought about this until 2000. It's a bit silly, but it's very cool and quite useful to do this. Cool. So now I'm gonna change tack a little bit. So we got this technique, we got this method for doing this thing. It has a very clear problem. So let's take this data. When you look at this data, you see that, cool, this looks like some one-dimensional thing embedded in a two-dimensional space, and there's some noise around it. What I said that locally this distances make sense, so I zoomed up locally, and it looks like that, right? It just looks like a mess. So your algorithm, if it basically has this tiny glasses on, moving around here, only sees this. It's kind of hard to generalize from this to that, right? But all of these algorithms, the type of algorithms that we took, that I just talked about, based on local measurements, are going to be very, very susceptible to noise. And this is an issue. So instead, we can think about taking a slightly different approach to this problem. And that is saying, instead of saying what we've done so far, of saying, I got this data, I'm going to come up with some form of measurement on this data that respectfully follows the manifold, and then I'm going to apply a technique to go here. Instead, we can say, well, let's say I got this, and I specify what's actually happened is I've taken this data, I've applied a mapping to this data and made it look like this. Can I now find the mapping back? Right? That's a different way of thinking about the problem. So we're thinking about this as a generative model instead. So something that I don't know that maps to something that I've observed. So this is a really, really ill-defined problem. So think about it like this. I'm here right now, and I still have hair, but I'm here right now. And the question is to you, how did I end up here? F. And where did I start off with? X. Those are the two questions that you need to solve. That's quite hard to do, right? It's a very, very ill-defined problem. So that's what the generative approach tries to address instead. So to do this, what we do is that we instead think about, so in order to regularize this problem, to be able to find a solution to it, we need to place priors, or we need to place beliefs on what we think are sensible starting points for F and X, right? And you will probably have quite a good idea where I came from and how I traveled here this morning. I probably didn't come from Alabama, and I probably didn't ride a bike from Alabama, right? So you have a notion of this. So can we take those kind of beliefs and put into a model so that we can learn a visualization from it? And to do that, we would have to do something like this. We would say that we would have the generative model, so P of y given f comma x would be saying, if I know how you traveled here, f, and where you started, then I could generate the data. Then I would have to have a belief over what I think the path to get here, f, and a starting point x would be. So now the problem with this is that if I would, in the general case, try to solve this to get the object distribution over the path traveled and the starting point, this is computationally intractable. You can't solve this. No way. So that's going to lead us to the notion that we're going to talk about on Friday. How can we look at these types of models to approximate them, right? And that's kind of the final step to lead you, as we said, things to think about when you take further courses in machine learning. So just a hint on this, if we do, so this is just a nice way, I hope, of connecting everything that I've said. If I would say that the mapping itself would be linear, so I take something and I map it linearly down to this observed space, and I would say that the starting point is a Gaussian, I would recover exactly the same solution as everything I described before in the MDS setting, where I have a global similarity measure between something. So this is the other way of deriving MDS or deriving PCA. It leads to exactly the same thing if I make that assumption. So I'm going to wrap up, but basically, the key thing that I wanted to try to get across is that when fitting models, you really want to get an intuition for data. Your data will generally be very high dimensional. So how do you think about high dimensional data? Well, it's very, very, very hard, right? So now what you would want to do, because generally the data itself, the canonical representation that we talked about, data is not going to have this many degrees of freedom. It's a characteristic of the parameterization of the data, not the data itself. So can you reduce the dimensionality to look at it? Well, MDS, very, very multidimensional scaling, very, very general, allows you to visualize some form of proximity relationship geometrically. It's super useful. PCA makes the assumption that the data is vectorial in itself by just diagonalizing the covariance matrix. These two things are equivalent. However, this one does not require you to have vectorial data itself. This is the first thing you should ever do as soon as you see data. As soon as you have data, you should always apply PCA to it. First thing, always do Eigen decompositions of the covariance matrix. So, always do PCA. Second thing is, these matrices, if you look at gram matrices, distance matrices, covariance matrices, if data is much higher than 2-3 dimensions, you can still, after a while, start getting a notion by looking at something and seeing, oh, I kind of have an idea of how this varies. That's a skill that's very useful to get. The other thing is look at just projections of the data. There's something in pandas called scatter plots, which allows you to give, got a 10-dimensional data set, it will give you every dimension against every other dimension. So you get a 10 by 10, you can start seeing, oh, these covariance this way, these does not, and so forth. The other thing, which I think is really useful, is to look at neighborhoods to see how smooth your data set is. So what I'll do is I'll take, if I have some high dimensional strange data, I'll take a data point, and then I'll take its nearest neighbors, and I'll keep plotting them, the closest one, the next closest one, and so forth. And when I see that they stop making sense, then I'll be like, okay, that's about the scale of where something is smooth, right? So say I take an image database, and I have lots of images of Selma, right? So I'll be like, cool, Selma, the closest one is Selma again, but the fifth one's a cat. And I'm like, whoa, now we're completely off the scale here, right? That's another notion that's really, really useful to start thinking about how dense your data set is and so forth. Cool. So next time then, we are going to look at effectively how we can do generative models for these kind of things. And basically, all of this becomes intractable straight away. And then we're going to look at how we can approximate effectively this integral and seeing different means and ways of doing that. Cool. So with that, I'm going to wrap up. And is there any questions? Shoot.
Can you go back to the slide where you had the picture?
Yeah. There.
Does this assume that I is over there and there? So
Oh, sorry. Now I'm just going to stop recording. What happened now? You stop cloud.